Hello, hi, this is Mr. Aya and welcome to my channel. This tutorial is all about coding convolutional neural network using Torch and other open source libraries. So we're going to code a convolutional neural network, in fact different convolutional architectures for a dataset in which we have to classify monkey species. So let me first show you the dataset that I'm going to use. It's an open source dataset from Kaggle. Let me just quickly type monkey species. So the first dataset that you see over here is what we're going to use, 10 monkey species. So the problem statement is like we have bunch of images with us, and that images contains monkeys of 10 different species. And guess what? It has also labels. So it's a pure supervised problem. So we're going to apply some open sourced famous architectures like ResNet, EfficientNet, and other. And even we'll try to come up with we'll see how we can write our own architecture. So let's quickly add this to our Kaggle notebook, and that should be it. Yes, we got it. So let's start by importing few Torch based dependencies like Torch and NN, of course functional, and you need Atom optimizer while optimizing your loss function, and the old classic dataset and DataLoader classes. And this part of the code is just for importing NumPy and OS and other simple Python libraries which comes handy while doing matrix multiplications, visualization, etc, etc, etc. So let me just run it. So it's done. Let's move forward, and these two lines are just I'm collecting trying directory and validation directory in respective variables that you can simply do by copying the file path. So before moving forward, let me just show you how our particular data set is distributed. So we have a folder called training, inside which there is another folder, in fact only one folder, which is again named as training. Inside that we have 10 classes, 10 different folders representing 10 different classes. Inside each of these folders we have images of monkeys. Similarly, similar to training, we have 10 different folders inside validation as well. So this is how our dataset looks like. So we are just grabbing the train directory, which is like the very inner folder training, and similarly we are grabbing the validation folder. Now glob.glob, we are passing it into the glob.glob, which fetches all the files that are ending like this. So it's like, okay, just go into train directory and select all the folders that you have inside that, and select all the files that you have inside that, inside of each folder that you have selected. So this fetches us all the image directories that you have inside each of these folders. So let me just run it and print train image directories so that we'll get a better picture. Okay, let me comment this part for time being. Okay, as you can see here, you got a list of strings, a list of directories to be specific. So you have N8, and you probably have N1, and all kind of folders, lot of things in N1, lot of things in N7. So it's like, as we have discussed earlier, we're getting all image directories. So we'll have to print the unique labels as well. Unique labels in this case is just N0, N1, N2, N3, so on up to N9. So I'm just fetching it using os.list directory. os.list directory returns a list of folders that you have inside a present directory. Okay, so we have directories of all train images and the unique labels. Similarly, we have directories for all images in validation. Okay, so since the dataset is pretty huge, we cannot load the whole dataset into RAM, so we need a dataset. I mean a data loader class. So before writing a data loader class, we need something called dataset. So it's like a class which is inheriting dataset into it, and as a Python class, of course, it expects you to write a constructor, and rest of the two functions that you see over here are expected according to the torch format. So let's fill this one by one. So the first method is init, where you just take all necessary inputs. So I'm going to take all the image directories over here, as you can see. And similarly, I have to take all unique labels. So labels is a list of unique labels. Okay. So length, this function, we have to return the length of our data set, so that while you actually mention the batch size, Pytorch will know how many iterations it should do on your present data set. So self.train directories, since it's a list, it's going to work. And get item, so get item function, we have to assume that it takes one ID, and depending on that we have to generate one data point. So after that, you will wrap this dataset class or dataset instance of the class inside DataLoader, which will tackle the batching. So let's quickly write get item. So first things first, we have to select the image directory, which can be sliced from your self.train directories, and label is okay, sorry, label is in image directory itself, right? So as you can see over here, let me just print it in a different cell. Sorry, I think it's my bad, it's a typo. Okay, so it's like N8 is your label, so you can split this whole string using the slash, and it's last and it's the second from the last. So let's just do it by writing label is equal to train image directory dot split, and just pick the second one from the last. And this is a string, so let's convert it to integer. So this is your label. Now let's quickly read image. Maybe I'll just write img, and let's use cv2 for reading the image directory. And image is equal to, let's just resize it to some standard size. So the size that I'm going to use over here is 256, 256. You can experiment with the different size, it's perfectly all right. And since it's a classification problem and it's a multi class classification problem, let's just one hot encode our label. So for that, I'll quickly write another function here, get one hot encoding, which takes our categorical ID and converts it into a one hot encoding. So how can we do that? Let me just declare one hot, and it should be similar to self.labels. Since we have all the possible labels in self.labels, it should be of same length. So one hot is equal to, or else I have even more easier way to do this. We can just do a Boolean comparison and compare it convert it back to integer. So it's like just comparing cat with your, since self.labels is not a numpy array, I'm just fetching it into numpy array. Maybe I can do this over here itself, so that I need not do it every now and then. So I just need to compare it with cat. So wherever there is cat, we're going to get 1, and wherever there's no cat, we'll just get zeros. So let's return this. So let's return this. So let's return this one hot encoding, and we can quickly get label, or let's use a different variable name, one hot, by calling get one hot encoding. As you can see, every other function that I write over here is just for my comfort. So there is no rule that you have to write it as a separate function, but these three methods are really necessary if you want to complete your dataset class. Okay, so let me pass label into it. So you'll get one hot now. And now, since image is right now it's a numpy array and channels are at the last dimension, so but in PyTorch we follow channels first notation. So let's just transpose our image by the last dimension should come first. That means 2 is our last dimension, so I'm placing it in the first position. Rest of them will remain the same, and we have to fetch this as a tensor, and let's use floating d type. Similarly, label should also be fetched as a tensor. Sorry, my bad, it's one hot that you have to fetch as a tensor. One hot and torch.tensor of one hot, and d type is torch.float. So that concludes our get item part. So let's just return it. Before returning, I'm just dividing it with 255 so that it will be normalized. That's it. And I just want to print my train image directory. I'll just say y in a couple of minutes. Okay, sorry, it's a label, so it's not an integer. The label is the name of the folder, so of course it's not going to be an integer. And there is, okay, it's a silly typo, self.labels. Great. So n3 is my folder name, that this image belongs to n3. So let me print my unique labels list. So n3 should be in my last position. So that's what happening here. So the one hot encoding is true, and similarly, as you can see, the image is also coming fine. I've just for sake of visualization, I have transposed the tensor that you get here back to channels last notation. Okay, so that concludes our dataset part. So let's quickly wrap this into data loader. So you just need to pass dataset into your data loader, and you can of course mention the batch size and other stuff. Okay, so how do you make two different datasets? You just have to call the dataset class 2 times with corresponding arguments. With that, let me just run this. So it went fine, and let's get into the convolution. So if someone is not aware of convolutions, this is the brief animation on how convolutions will work. Okay, so this is our input image, and the sliding window over here is called filter. So this sliding window will scan all of the image and converts that big input image into a smaller encoded matrix or a feature. So all the features are spotted and a new matrix is computed. Okay, so it's a kind of transformation. So if you are stacking these convolution layers one upon the other with many filters, that is what we call a convolutional architecture. So quick formula, quick revision about output size of a convolutional layer. So this is how it is. If you have input size, and if padding is what you add to the edges, as you can see in the dotted lines. So most of the times we won't be using padding until and unless you want your output size to be similar to what you have at your input. So input size plus 2 into padding minus filter size by stride plus 1. So this is the quick formula that you need to use while making up or coming up with a new architecture. This is the one you have to keep in your mind. Okay, with that, let's just jump into the architecture. So as you can see, I again have a boilerplate of how our neural network should look like. I named it as monkey species classifier, and it again expects 2 different functions. One is init, again the constructor of a Python class, and a forward function, which in which we have to declare our forward pass. Okay, so let's get started. So as you can see over here, I'm taking num classes as my input to my constructor, because it makes it helps us to make the architecture more dynamic. So if you are using the same code on on some other data set, you need to make minimal changes. That's the idea. So self.num classes is equal to num classes, and before doing that, of course, you have to call the super function. Okay, it's done. So here now you can start declaring your own convolutional neural networks, convolutional layers, which can be easily done using nn.conduty. And a nice documentation just popped up. As you can see, it takes in channels, out channels, kernel size, stride, padding, yada yada yada. But in channels is like the dimension, the channels dimension of your input matrix, and out channels is like the filters, number of filters that you want to apply for that particular convolutional layer. So since it's an RGB, of course there will be only 3 channels. Let's say you want to transform it to some, let's say 64 channels maybe, I don't know. And kernel size can be 3,3. You can choose among 3,3, 5,5, 7,7, and many more, but this is the standard practice. People just pick 3,3. And it's a hyperparameter, of course. There's no hard-coded rule that you always have to pick 3,3. And kernel size, you can again, okay, kernel size I've already picked it up. Filter size is kernel size, my bad. And stride can be 2 or 1. It's again a hyperparameter that you can tune. Okay, stride basically means here, as you can see, the window is just moving by 1 block for each iteration, but if you are putting stride as 2, it skips 2 columns at a time, like it moves by 2 units for each single iteration. Okay, so you can stack different convolution layers like this and come up with your own architecture. But as far as this tutorial is concerned, I'm going to use something more efficient. Okay, these are the 3 famous architectures in image domain. So we have ResNets, EfficientNets, and EfficientNet v2. So I quickly linked all the papers to the corresponding network architectures. So if you're interested into how the architectures are formed, what exactly ResNet has and all, you can check the links. I'll pin it in description, and I'll share this notebook with you, so feel free to check that out. Okay, so we can take a pre-trained model from one of these and fine-tune it on our toy task or on our toy dataset. So to that, a quick shout out to for that we have to use something called timm, which is an open source library which has a lot of computer vision models, not only these 3 families but a lot more. And the best part of this library is we have pre-trained weights available in the library, so you can just quickly access them and fine-tune it on your toy dataset. So a big shout out and all credits to Ross Whiteman, who is the creator and author of this repository. So let's just quickly go up and maybe install. Maybe I'll just take the imports and move it down a bit. And let me quickly install timm library using pip install. And I'll quickly import it. I'll quickly add it to the imports that we made previously. It's going to take a little bit of time. I think it's done. Yeah, let's run it. Okay, cool. It went really well. So let me just show you how vast this timm library is. I'll bring up a new code cell for that, and let me print, sorry, list models. As you can see over here, you have plenty of models and variants of each of these architectures like ResNext, ResNet v2, SU ResNet, swing transformers, vision transformers, efficient at v2s, whatnot, a lot. So I'll just, let me just print the length of this models list. So you have around 889 models along with the pre-trained weights on ImageNet, which is not a joke, and this is a big thing. So let's just take one of these. For time being, I'm going to grab some ResNet, most probably. Let me just go to R. Okay, here it is, ResNet. Okay, here it is. So just for my comfort, I'm picking ResNet 34 because it's a bit fast, it's light in weight. So all you need to do is self.model, timm.create model, and give the string, give the model name as a string, and by default pre-train will be false, so let's just edit it back to true. That's it. You have your self.model now, and you can quickly do a forward pass with the model that you created right now. So written self.model of capital X. So this code over here creates the instance of the class that we have wrote, and I'm just pushing out a dummy tensor. I'm just pushing out a dummy tensor over here and checking the final shape of our model's output. So it's downloading the pre-trained weights. Sorry, my bad. Okay, here it is. So as you can see, the final output size is 1,1000, which is like having 1000 classes or classifying 1000 classes in your dataset. But on the other hand, we have only 10 classes on our dataset. So this 1000 is because these models are trained on ImageNet. So of course that will be like having thousands of classes. So that's why the final output size is 1000. So let's just edit it. Before going further, let me just show you the model architecture. So this is ResNet, and there are a lot of blocks, basic block, and there is a sequential block where you have a basic block again inside that, and it's like stacking of lot of basic blocks. Okay, if you scroll down to end, you can see a fully connected layer having out features as 1000. So you just need to replace this particular fully connected layer, right? So let's just do it. Self.model.fc, since that is what it's being named in our model fc, and let's go back and do self.model.fc is equal to nn.linear of, so input is like self.model.fc.input, sorry, in features. So it's like I'm going into fc and taking the in features, accessing the in features variable. Since even if you replace the model with a new dense layer, still the input features will remain the same because it comes from the previous layer. But now out features will vary, which will be num classes. This should be it. As you can see over here, you have now a size of 10. Pretty good. Yes, great. So let's just move forward and finish rest of the code. So this is just optimizer. We're taking Adam and mentioning the learning rate, and parameters are model.parameters because these are the parameters that you want to optimize. And loss function, since it's a classification problem, you're going to code cross entropy loss, right? So let me quickly, since y prediction at times can reach extremes, which will not be good because we'll be pushing y prediction into logarithm. So if it's y prediction is 0, logarithm will go to minus infinity, and since Python can't handle minus infinity, it's going to replace it with nan, and which is going to be really messy. So let's just clip our y prediction before computing loss between a very small epsilon and 1 minus epsilon, 1 e minus 8. Right, now loss is equal to y true star torch dot, sorry, log of y prediction, and l dot. So we have 10 classes, so let's just do the mean on 10, and sum on 10, that is our last dimension. So dim is equal to -1, and again, so now it's a 16 dimensional tensor because our batch size is 16. So let's take a mean of that 16 numbers that we got, and written, don't forget minus because this is a cross entropy loss which contains minus here. Okay, let me run that. Cool, so it ran without any error. So for now, like until here, we have just coded all the necessary components like data loaders, dataset, loss functions, optimizers, neural network architecture. Now we have to put all this together in training loops. So you can see a very simple training loop over here, which is getting iterated for 10 times, and every time I'm just executing one single function, I mean two functions, one for training, one for validation, and it's like just printing the metrics and the loss values at that particular epoch. And this if condition is for saving your weights. So I'm just tracking the accuracy using a variable, as you can see over here. So whenever there is an improvement in accuracy, you'll be just saving the model. So this is the very simple explanation of the for loop that we have written over here. So let's just go back to the important functions that we have to fill up, which is the training and validation for one epoch. Okay, so training on one epoch takes data loader, optimizer, loss function, and length of data loader as well, because we want to compute the average. Okay, let's start writing. First things first, let's don't forget that we need a progress bar. To get a good progress bar, let's wrap it around TQDM, and for sake of loss function, I'm initializing a variable. For sake of accuracy, I'm initializing another variable, and now we can loop through the whole data set. So for I x comma y in the data loader, okay, let's also have enumerate since I'm fetching the counter. First things first we have to get the y predictions. We can do it, okay, we can simply push x into our model, and model is a global variable over here. A quick thing to note at this point of time, because I did not pass model as an argument. You can even pass model as an argument and receive it back in the return statement, but to simplify the process, I just used it as a global variable. So model of x will give you the y prediction, and now let's compute the loss function. Loss is like loss function of, we have taken y prediction first, so y pred comma y. Okay, So again, there are three important steps that we have to do over here. First thing is like zeroing out the gradients. This is really important because you don't want to have the residual gradients of the past iteration. And second step is computing gradients, which can be done using L dot backward. And the final step is to update the parameters by calling optimizer.step. That's it. So let's add loss to our capital L. Sorry, let's rename it as capital L then. So let's add L to L, and let's compute the accuracy. I mean, let's first add how many correct predictions we have in this particular batch. So it's like y prediction. Before comparing anything, you have to fetch this into NumPy. Before converting it into NumPy, you have to place it on CPU if it's not, and then detach from the computational graph and then put it on NumPy array. Similarly, you can do it for y as well. y.cpu.detach.numpy, and I'm just doing a equal to operator over here so that I'll know how many matches are there in both of these. And remember, y prediction is in probabilities, so you have to compare the maximum. Similarly, these are one hot encodings. Again, I'll take the numpy.argmax on the last dimension. First is a batch dimension, last is the class dimension. So now you'll be getting an array where there'll be a 1 when y prediction and y are matching, where there'll be 0 when y prediction and y are not matching. So you just need to do a numpy.sum on it so that you'll know how many of your predictions are matching with your ground truths. And return average of loss, so which is like L by length data loader and ACC by length underscore data loader. Fine. So that's all about training loop, and now let's get into validation. Again, we need something for loss and accuracy. I think you just don't need to write it again. You can take the same thing and just copy it, but the only thing that changes is you don't need optimizer, you don't need to calculate gradients anymore. So just take out those three important steps that you have made in training procedure. Okay, so that's it, and let's just return again loss divided by length of data loader and accuracy by length of data loader. So that's done. Let's just run it. Okay, a quick thing that we have to note over here, we have forgotten to comment the print line in our data loader back then. So let me just go there and comment this out just for better visibility of training procedure. Rest of the things don't change. Let's go back and run the training loop. Okay, as you can see over here, it's taking around 6 minutes to finish one epoch. The estimated time is 6 minutes. So let's just place this whole code on GPU. Okay, so how do we do it? As we have seen in the last tutorial, first thing you have to do is you have to turn on the GPU on whatever platform you are using. And let's go back all over to the beginning, and let me define a variable called device. So it will be CUDA if CUDA is detected, or else it's going to be normal CPU. Sorry, I have to first rerun the libraries. Come on. Sorry, I have to again install pip. And let's just see by printing device whether it's going to be CUDA or CP in this case. Let's wait for some time. Yeah, it's CUDA as you can see over here. So let's run rest of the code as we have. And three important things that we have to remember when using CUDA is we have to place the model on CUDA, we have to place the input on CUDA, we have to place the ground roots on CUDA. So these are the three important steps that you have to keep in mind while placing your neural network or your training procedure on CUDA. So let's place our model onto CUDA just by writing to device. Okay, if I run like this, I'll surely get an error because model over here is placed on device, but Torch.zeros, which is the dummy tensor that I've created there itself, is not placed on Torch CUDA tensor. So as you can see here, so input type is float tensor, but weight type is torch.cuda.float tensor. So to avoid this, you just have to go back and place this particular input tensor onto device again. So now it should not throw any error. Let's see. Yes, it didn't throw any error. So let's move forward. And so the second step, we have to place the input and ground truths onto device again, right? So x.toDevice, y.toDevice. Similarly, just add the same thing while we are in validation loop. So these are the changes that you have to make. Hopefully this is going to run on GPU. Yeah, it's running on GPU. Now it just took 41 seconds. The estimated time is just 41 seconds to finish this whole epoch, which is a way more lower than what we have seen on CPU. So let's just wait until it finishes 10 epochs and let's see the best. There is a quick thing to add over here, which is f.softmax, because the output will be a two-dimensional tensor where the first dimension is for batch size and the next dimension is for number of classes. So you have to apply softmax on the last dimension to get the probabilities. After running it for 12 epochs, I was able to get a validation accuracy of 91% and train accuracy of 96%. So you can play around with this even more, like train it for more epochs, tweak the network architecture. You could have used ResNet 50, EfficientNet, and even other architectures that we have inside this timm library. So feel free to experiment with it with that, and do tell me in the comments about the performance of your model. And stay tuned. If you didn't subscribe yet, please do subscribe, and if you have friends and family who are interested in this stuff, do share my video to them as well. Thank you so much. Bye bye.